Good afternoon, everyone. We'll start the session by 3:05. Let us wait few more minutes for others to join as well. Thank you. So let us start now. So this is Computational Fluid Dynamics course, NPTEL course problem solving session. So we are now in week 7 session. So the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, and while myself, Ankara Kartiga, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So this session is happening every Saturday from 3 p.m. to 5 p.m. So let us start now. So this is just to give you an overview of the course layout, and this is like we have almost covered 6 weeks of problem. I mean, this week we'll be covering 6 weeks problems as well. 5 weeks assignment problems we have solved, and sixth week practice problems also we have solved till now. And what we have covered is like introduction to the calculation of flow in a rectangular duct, and calculation of fully developed flow in a triangular duct, and derivation of equations governing fluid flow, and equations for incompressible flow and boundary conditions. And in week 5 it was about basic concepts of CFD like finite difference approximations, and in 6th week it was about consistency, stability, and convergence associated with those equations, like how to get uh, our desired results from the basic governing equations. And in seventh week, it is about all about dealing with the Navier-Stokes equations for compressible flows and how to get the solution for the same. And eighth week, it is about solution of Navier-Stokes equations for incompressible flows. And in the last few weeks, it is about solution of linear algebraic equations, basic methods and advanced methods. And then finally, it is about basics of finite volume method. Like till now, we are almost like seeing about finite difference method, while in week 11 it will be about introduction to the finite volume method, including the grid generation and turbulent flows and turbulence modeling. So finite volume method, we have just seen a brief outline on the week 2 problems itself. More will be dealt in those theory classes. So the theory, I mean, in the course content is given by the NPTEL, like 5 hours, 5 lectures per week or so. And for aiding in the problem solving, this every Saturday, and one more session on Tuesday is held by some other TA as well. Like we are discussing the problems for those sessions. So now we'll go to problems for this week. The first problem is the unsteady two-dimensional advection equation with no diffusion is given by option A, dou f by dou t is equal to dou f by dou x. Option B, dou f by dou t plus dou u by dou x plus dou v by dou x is equal to 0. Option C, dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. And option D, it is dou f by dou t plus dou f by dou x is equal to dou square f by dou x square. So here we should first see what is given in the question. So in the question, first statement is unsteady system. So for unsteady, we mean we will be having dou by dou t of something. So if it is a steady system, that term would be approaching 0. So that would be absent in the equation. But here it is given as unsteady system. So dou by dou t would be present in the answer. So on that basis, we can say that all the 4 options are including the dou by dou t. Here it is dou f by dou t, where f is just some parameter. It can be velocity, it can be time, whatever. And next is two-dimensional advection equation. What is given? Two-dimensional equation. So it would be varying with respect to x as well as y. So on that basis, like option A, it is involving only one dimension, that is x dimension. So it would not be the desired possibility. In option B, it is like x and x, and in option C, it is x and y, and option D, it is x and x square. So like on seeing that only these two are including x and y, so the unsteady two-dimensional advection equation with no diffusion is given by. What do we mean by diffusion? Like in which the that parameter travels through the system, like the value of that parameter travels through the system by means of diffusion. So that is not absent, that is absent in the give. If that is absent in the equation, how the equation would be? So generally the diffusion term is given by dou square of something by dou x square or something. So that particular diffusion term comes in this form. So this is not the answer because it is having diffusion. While we must check between B and C. So because the advection terms would be including dou by dou x of something, dou by dou y of something, because we are having again two-dimensional terms. So x and y would be present. And here since the parameter or the variable is f, it should be uniform throughout. Like dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0 is the proper answer. Because in option B, it is like, although it is starting with a variable f, here it is changing between u and v. So like if it is like a velocity variable, and the first term should also be a function of velocity, that is dou by dou t of velocity should have been there. But since it is absent, the answer right answer to this particular problem is option C, that is dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. Answer is option C, because dou f by dou t plus dou f by dou x is equal to a times of dou square f by dou x square. This is the general equation in one dimension. So here we are having advection term, unsteady term, and diffusion term as well. So this is the advective term and this is the diffusive term. So unsteady 2D advection equation would then become, we would be involving one more dimension in this particular equation and removing this particular term. So it is dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. Now we'll move on to question 2. In question 2, it is mentioned that the unsteady one-dimensional diffusion equation is given by for a greater than 0. So in the previous question itself, we saw the generalized equation dou f by dou t plus dou f by dou x is equal to a times of dou square f by dou x square. So here it is same equation, but it is a diffusion equation. So the unsteady one-dimensional diffusion equation is given by for a greater than 0. So we all know that it would be dou f by dou t is equal to a times of dou square f by dou x square. We'll just see the option, and in option 1 it is dou f by dou t plus a times of dou square f by dou x square is equal to 0. Option 2 it is dou f by dou t minus a times of dou square f by dou y square is equal to 0. And in option 3 it is dou f by dou t is equal to a times of dou square f by dou x square is equal dou f by dou t is equal to a times of dou square f by dou x square. So here it is mentioned that a is positive. So if a is positive, the general equation is such that dou f by dou t is equal to a times of dou square f by dou x square, where a is positive. So this is the right answer. If we take this term to the left, from the right hand side to the left hand side, it would be becoming minus a. So since it is absent in the first equation, this is a false equation, and in second equation it is rightly mentioned as negative. Dou f by dou t minus a times of dou square f by dou y square. Here it is in varying with y direction. Here it is varying with x direction. That is the difference. But in general, it is the unsteady one-dimensional diffusion equation is given by for a greater than 0. So remember always that diffusion equation would be having dou square by dou x square or dou y square. So that term is the one associated with the diffusion. So here 2 and 3 are right because it is given a is greater than 0. 2 and 3 statements are right. We'll just look at the options. So in option A it is 1. Option B it is 1 and 2. Option C it is 1 and 3. Option D it is 2 and 3. So as we have seen that the right answer is option D, 2 and 3 is the right answer, because like it is generalized forms dou f by dou t is equal to dou square f by dou x square into a or something. So here this is the right format, so we are taking it to the left hand side and we are having this. So the from this generalized equation, again here in the question it is mentioned that a is greater than 0. So here it is 2 and 3 are right. Answer is option D. And yeah, here dou f by dou t plus dou f by dou x is equal to a times of dou square f by dou x square, and it is advective term, so we are removing it, and therefore unsteady one-dimensional diffusion equation is given by dou f by dou t is equal to a times of dou square f by dou x square. So this is a generalized format, and we are taking the a to the other side. We are getting one more format. This is 1 and this is a. We have taken it to the other side and we have got this equation. So these two are the right answer. Because it is given a as positive, we have used we have taken we have eliminated the first option basically. So now let us move on to question 3. In question 3, it is mentioned that which of the following is true about Courant number? Statement 1, Courant number is a condition on the stability of numerical scheme. 2, high value of Courant number is desirable for consistency. 3, Courant number condition does not arise for elliptic problems. So basically, what is Courant number? Courant number is nothing but we have some criteria, like from Von-Neumann analysis or something, we'll be getting some criteria. So basically, the system should satisfy that particular criteria in order to achieve the stability. So it is a condition for attaining stability on a numerical scheme. So statement 1 is right. Courant number is a condition on the stability of numerical scheme. So it imposes certain criteria like For example, delta t by delta x should be greater than some values, or it should be less than values. Mostly it would be less than some desired values. So we will be setting a maximum for the Quran number, and during the calculation point it should always be less than 1. If it is going above 1, the system would not be producing a true results, and it would be diverging soon. So first statement is a right statement. Quran number is a condition on the stability of numerical scheme true. High value of Quran number is desirable for consistency. It is the false statement. On the other hand, we desire a low value of Quran number in most cases. For getting consistency, Quran number is less than certain value is always preferred. Like it would be like in wave equation or something diffusion equation, it would be like a delta t by delta x is less than or equal to 1. So like not exactly, but it would be similar to that, so that on the basis of mesh refining and time step adjustment, we would be bringing the Quran number to a less than certain value, like v into delta t into delta x. So it would be how much it is, how fast it is propagating, this calculation is propagating. So we can adjust the system calculation speed based on the Quran number. Like, so we should be modifying the time step, and if needed we should be modifying the mesh size as well if the velocity is fixed. So one such example is that, so high value of Quran number is not desirable. So second statement is a false statement. In third statement, it is mentioned that Quran number condition does not arise for elliptic problems. This is again true. We will see how in the next slide. So from these options, 1 and 3 are only right ones. So it is option A 1, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. Since second statement is false, we are going with first and third statement. So basically high number of Quran number is not desirable. So in order to understand what Quran number condition, why Quran number condition does not arise for elliptic problems, we'll see in the next slide. So right answer is option C. So Quran number is how much information travels across a computational grid in unit time. So basically how much information it is transferring or traveling across a computational grid per time step. So how can we mention that V into delta t by delta x? It therefore depends on dt and dx. So elliptic equation is of the format del square u. So dou square u by dou x square plus dou square u by dou y square. So this is the format of the elliptic equation. So here it is like depending only on x. So we cannot give a value for the Quran number for the elliptic equations. Therefore, elliptic equations Quran number is not desired. And like you can also remember, like elliptic, it would not be marching with time. We would be solving it simultaneously, the equations from the characteristic equation, that part. So therefore it Quran number condition is not required for elliptic equations. Quran number condition does not arise for elliptic problems. So third statement is again true, because the equation is of this particular format. There is no need for time. So like condition is not required arise. It does not arise for elliptic problems. So we'll go to question 4. The equation should be simultaneously solved to get the solution in the elliptic equations. So it cannot be obtained by matching. That's what I said. Like in characteristic equations, that part itself we have seen like how the like zone of dependence, zone of like if how the boundary conditions were all given like that we have seen a map. So in the elliptic solution of the elliptic equations, what we have seen is that those equations should be solved simultaneously. It is not like a marching problem, like one time step to another. So since it is not a marching problem, there is no need for Quran number. So now it is question 4. In question 4, it is given that for the equation dou f by dou t plus a dou square f by dou x square is equal to 0 to represent unsteady one-dimensional diffusion equation, the value of a should be. So here the equation is such that it is a reverse of the question asked in second problem. So here it is, instead of asking, giving A as positive and getting the proper equation, what we are given is, we are given the equation. So equation is that dou f by dou t plus A times of dou square f by dou x square is equal to 0. So since that, if this is the equation, what would be the value of A, so that it can represent one dimensional diffusion equation. So one dimensional diffusion equation is that dou f by dou t is equal to A times of dou square f by dou x square. So if it goes to the other side, the term should be positive. So if it needs to be positive, A should be positive on the other side. So in the left hand side, it needs to be negative. So we'll see first. One is A greater than 0, second is A less than 0. And option A 1 only, option B 2 only, option C both 1 and 2, option D A should be an integer. So here the right choice is A should be less than 0, because the equation is that dou f by dou t is equal to A times of dou square f by dou x square. So at that particular point, A should be positive. So if it is in this particular side, A should be negative, obviously. So answer to this is option B, that is 2 only is the right answer. Now we'll see question 5. In question 5, it is asked that which of the following equations represents unsteady two-dimensional advection equation with no diffusion. So this is again the same problem, like here it is like unsteady two-dimensional advection with no diffusion. So the first question was about one-dimensional advection equation. No, I think it is the same question with no diffusion. Okay, it is just the same question with a different format. But it is basically dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. Second one, it is dou f by dou t plus dou u by dou x plus dou v by dou y is equal to 0. Third one, dou f by dou t plus dou f by dou x is equal to dou square f by dou x square. So by now we should be knowing that this is a one-dimensional equation with advection as well as a diffusion term, and this is a two-dimensional advection term, unsteady, all are unsteady equations, and here it is just a mix-up of all these things. It is not a proper one. So first one is the right answer, that is option A 1 only is the right answer. B is 2 only, C is 3 only, option B, option D none of the above. So answer to this particular problem is option A. It is the same as the first question. Instead of selecting choice from the options, here we are given to select from the like mix up many equations are given, we are asked to choose one or multiple things from that. So but basically the answer is the same, that is dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. That is, first statement is alone right, so option A 1 only is the right answer. So in question 6, here we are dealing with the problem. It is figure 1. So here we are given a figure. So here it is that figure 1, initial condition and computed solution. So this is the initial condition that we have given, that is a solid line, and there are some pointed lines. So those pointed lines are the computed solutions at 3 different times. One is at 0.05 seconds, another is 0.2 seconds, another is 0.5 seconds. At 3 different times for a one-dimensional unsteady case. So here it is mentioned that it is a one-dimensional problem and it is an unsteady problem. So it is like traveling, and these are like 0.05 seconds, and this is at 0.2 seconds, and this is at 0.5 seconds. So one thing we can see from here is that it is a diffusive error, because like it is just spreading out. We'll see what the question is. First, consider the numerical solution and the initial condition given in figure 1 for a one-dimensional unsteady problem. So it is same as that. In figure 1, there is a numerical solution and initial condition. This is initial condition, and these are solution at 3 different times. And for a one-dimensional unsteady problem, which of the following statements is true about the partial differential equation that is being solved numerically? So there are some statements we need to identify which of them are true about the partial differential equations that is being solved numerically. So we'll just read the statements. Statement 1, it is PDE is 1D unsteady wave equation. PDE is 1D unsteady diffusion equation. And third statement, it is PDE is unsteady convection diffusion equation. So what happens is that the first statement is that PDE is a one-dimensional unsteady wave equation. So here it is a wave equation. So the statement is true. Second one is given that PDE is one-dimensional unsteady diffusion equation. So here it is false, because if it had been one-dimensional uh, unsteady diffusion equation alone, there would be no convective movement. If there is no convective movement, only dispersion, that is a diffusion of that particular wave, would be taking place. The convective, that is the whole movement, will not be taking place. So this particular problem, since it is like moving on the whole also along with diffusion, it is not a PDE one-dimensional unsteady diffusion equation. Rather, in the third statement, it is given that PDE is the unsteady convection diffusion equation. This is again true, because here there is convective motion is as well, is taking place as well, and the diffusion is taking place as well. So like in this is like diffusion motion. Like here you can see that the wave is tall, and after that it has diffused so much. So it is, and then it has moved so much also. So it is convective diffusive equation, and also it is a 1D unsteady wave equation. So it is, both of them are true. Initial condition and computed solution 3 different times for a one-dimensional unsteady case. So it is a 1D problem, an unsteady problem, and it is a wave equation problem, and also it can be a convection diffusion equation. Why it is a convection diffusion equation? Because diffusion, it is like the wave is spreading out, and also there is a convective movement as well. So it is a convection diffusion equation and not just diffusion equation. So the statement 2 is wrong, because it is mentioned only diffusion equation, whereas statement 3, it is including convection term as well. So statements 1 and 3 are right. We'll check out the answers. Option A, it is 1 only. Option B, it is 1 and 2. Option C, 1 and 3. Option D, 1, 2 and 3. So as we have seen, the answer to this particular question 6 is 1 and 3 are the right statements. So it is correctly given in option C, that is 1 and 3 only. So answer to this problem is option C. Yeah. Now we'll go to question 7. In question 7, it is asked that if the computed solution in figure 1 is unsteady wave equation, the numerical error is said to be diffusive. Option 2, it is dispersive. It is actually, if the computed solution in figure 1, that is figure 1 is in the last slide. So these points are the computed solution. So as we can see that it is getting diffused, it is not getting dispersed. Dispersed means it would be like some random, it would be moving at a different velocity. But if we can see that here, it is like the velocity is almost the same, that is at 1 meter per second, because here you can see that it is at 0.05 seconds, and it is 0.2 seconds, and it is 0.5 seconds. So here the motion is uniform, it is moving at a 1 meter per second speed, but the diffusion is there. So in 0.05 seconds the wave was like this, whereas at 0.2 seconds it is become like this, and 0.5 seconds it is like more dispersed, like not dispersed, more diffused. So this area, although it remains same with these three, it is more diffused in this one. For like, it is like, sorry, like what was like this at 0.05 seconds has become like this, 0.5 seconds, like it is at 0.02 seconds, it was like this, but in 0.5 seconds it has become more diffuse. But we can see that it is at the motion is like uniform, like it is moving 1 meter per second only. So it is not a disperse error, rather it is a diffusive error. Dispersive error means it would be like moving at a random motion and the velocity would not be the same. So it is like diffusive error. If the computed solution in figure 1 is for unsteady wave equation, the numerical error is said to be 1 diffusive, 2 dispersive. So 1 alone is right. Option A 1 only, option B 2 only, option C 1 and 2, option D insufficient data. So answer is 1 only, that is option A is the right answer, because it is only getting diffused and it is not getting dispersed. That is the reason. And now we'll go to question 8. In question 8, it is mentioned that for the one-dimensional wave equation, which of the following is true for FDBS explicit scheme? So the question is for one-dimensional wave equation, that is dou f by dou t plus dou f by dou x. Sorry, dou f by dou t is equal to dou f by a dou x into a. Which of the following is true for forward in time, backward in space, explicit scheme? So we'll options given are first order accuracy, option 2 consistency, option 3 conditional stability. So it is a one-dimensional wave equation. So if we are discretizing that equation in the form forward in time and backward in space and explicit scheme, what would be making sense? Like would it be first order accurate? Would it be consistent? Would it be conditional stable? We need to identify that. So I think all three are true. We'll see option A 1, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So answer is rightly option D, because it is obeying first order accuracy and it is consistent and it is conditionally stable. So we'll just see how that is in the next slide. Oh, sorry. Okay, I haven't given, I think. Just a minute. Just 1 minute, I'll be back. Yeah, the equation would be somewhat similar to this. It was not exactly the same. So for one-dimensional wave equation, which of the following is true for FDBS, that is forward in time, backward in space, explicit scheme. So statement 1, it is first order accurate. Statement 2, it is consistent. It is conditionally stable. So it is like 1, 1 and 2, 1 and 3, 1, 2 and 3. So we have seen it is 1, 2 and 3. So it is that unsteady one-dimensional wave equation. It is of the format dou f by dou t is equal to dou f by dou x into a. So this equation alone I am not particularly sure, but however the procedure remains the same, that dou f by dou t is equal to one equation is there and we are taking it to the left hand side, and now we are applying FTBS scheme, that is forward in time, backward in space. So for that particular reason what we are doing is dou f by dou t we are discretizing using forward difference approach. So it is Fi n plus 1 minus Fi n. So we are taking nth time step and n plus 1th time step divided by delta t is equal to a times of, now we are doing backward in space. So since it is backward in space, we are using delta x, and one plus, sorry, f a delta t by delta x would be sigma into f, sigma into this term won't come, sigma into fin, so 1 plus so this would be like sigma, like this would be going other side. So sorry, so what we have done is we have taken a delta t by delta x is as sigma. So this one we have substituted a, this delta t has gone to the other side, so a into delta t by delta x we have substituted as sigma, and now fi n plus 1 is equal to sigma into fi, so sigma into fi, minus f, minus will become plus because it is going other side, and after that it would be, yes, so sigma into fi n minus fi minus 1 n, so this f minus fi has gone to the other side. So on the whole how it would turn out, sigma fin is equal to sigma plus 1 plus 1. Yes, it should be something like this. No, I missed one more sigma as well. This will have sigma into plus 1, and this will have sigma as well. Now it is clear. We'll see. So what we have done is we have taken the 1D wave equation and we are discretizing using the forward in time, backward in space approach. So the equation we are getting is this: fi n plus 1 minus fi n divided by delta t is equal to a times of fi n minus fi minus 1, because we are using backward in space at nth time step, divided by delta x. So we are now substituting a into this delta t goes there. A into delta t by delta x is equal to sigma. So sigma is equal to a into delta t by delta x. So we have substituted it using sigma term. And now we are keeping fi n plus 1th term along this side. And we are taking the rest of the term to the other side. So it becomes fi n plus 1 is equal to sigma times of fi n minus fi minus 1 n plus fi n plus fin. And afterwards what we are doing, uh, is taken fin common and sigma plus 1 minus sigma times of fi minus 1 n. So what are the three statements given? The first one is, it is first order accuracy. So we all know that forward time and backward space. So we have used forward difference and backward difference for this first order equation. So they both are first order accurate. So it is obeying first order accuracy. The second one is consistent. Consistent is nothing but if we reduce the time step, it should be approaching 0 as delta t delta x approaches 0. The error should be reducing the going to 0. So here again, if we reduce it, the error terms would be becoming 0. So the system is said to be consistent as well. And last one is nothing but it is conditionally stable. So conditional stability comes in the form of, so first order accuracy is satisfied, consistency is satisfied, and last we have conditional stability. So conditional stability, here we are introducing the term sigma. That sigma is would be like, should be greater than or something for it to be stable. So I mean not greater than, should be less than something for it to be stable. So we call it conditional stability. So like a into delta t by delta x, so it should be, there should be a limiting factor for this, and therefore sigma should be less than a critical value, that we call it as a conditional stability. So since it is following some condition, we call it conditional stability. So on that basis, we have first order accuracy true, consistency true, and conditional stability is also true. So answer to this problem is option D is the right answer. Now we'll go to question 9. Similar question is coming one more in the next few slides. It is conditionally stable. In question 9, it is asked that which of the following statements is true about numerical errors. So the first one, they are inevitable. Second one, they can be controlled. Option 3, they can be eliminated. So numerical error is like, when we look at numerical errors, they are inevitable, because when we are using discretization, we are not solving it directly using analytical approach. So there would be some sort of errors always, because we are truncating it. Like when we use Taylor's approximation, there is a n number of terms involved in the equations. But depending on our need and our level of accuracy, we are truncating the equation. So on that basis, there would be truncation error, and this would be introducing, like, it is not an actual solution, so there are some other errors as well. So they are like inevitable, the presence would be always there, because we are not solving it directly. So they are inevitable. Option 2, they can be controlled. True, this is again true, because like we can control the error to some extent, like one, because if the error keeps on increasing, imagine the problem would not be proper solution, like the problem would not be getting a proper solution. So we would be doing something, and we would be getting a desired level of accuracy, and then it would be like not so error. There would not be many errors, there would be minimum errors, so that it would not be affecting the solution of that problem. So like we can adjust the grid size, we can adjust the time stepping factor. So on all these things would be reducing the numerical errors in the particular problem. So they can be controlled and they can be eliminated. This is false because we cannot eliminate the numerical errors completely. Like to some extent we can control them and we can reduce them, but eliminating them completely is not a possible solution. So 1 and 2 are the right ones. So we'll see the options. Option A, it is 1 only. Option B, it is 2 only. Option C, it is 1 and 2. Option D, it is neither 1 nor 2. So right answer is option C, 1 and 2. So answer is 1 and 2 because numerical errors are always there and they cannot be eliminated completely, but they can be controlled. Like their presence is inevitable in a solution because we are just approximating it by some means to get a desired solution and at a desired speed. Because imagine we are solving it completely, it would not be feasible to get the solution. So it is like inevitable, but it can be controlled. So now we'll go to question 9. Okay, this is just question 10. There is some mismatch in the questioning number, so don't worry. Question 9, it is about which of the following schemes is unconditionally stable for the unsteady diffusion equation. So it is 1, it is FTCS explicit, 2, Crank-Nicolson scheme, 3, Duford-Frankel scheme. So on looking at it, we can say that it is not unconditionally stable because explicit schemes are always most of the times conditionally stable. Like there would be like uh, variation. I mean, with change in time step, the solution would be varying. So it is not always unconditionally stable. There are some limitations and there are some conditions to control the solution and stability of the explicit equations. So first one is a false statement, and so second and third are right ones. Which of the following schemes is unconditionally stable for the unsteady diffusion equation? The answer is Crank-Nicolson schemes because it is an implicit scheme and we are solving it directly. So it is like to some extent the time step or the grid size would not be affecting the stability of the solution. Same is the case with Duford-Frankel scheme. So 2 and 3 are the right ones. Option A 1 only. Option B 1 and 2. Option C 1 and 3. Option D 2 and 3 only. So as we have said, first is a false. So we are left with 2 and 3 because first one gives conditional stability. Second and third gives unconditionally stable. So answer is option D. We'll now move on to question 10. In question 10, it is given that which of the following statements is true about the consequence of reducing the grid spacing. So first one, reducing grid spacing makes a numerical scheme more accurate. Second one, reducing grid spacing makes numerical scheme more accurate, more consistent. And third one, reducing grid spacing makes a numerical scheme more stable. Options are 1 only, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So I would say that reducing the grid spacing makes the numerical scheme more accurate. It would not be making more consistent or it would not be making stable. Like because in the consistency and stability would again depend on the time step factor also. But accuracy would be like if the grid spacing is reduced, the information propagated from one point to other, the distance would be high, so there would be error would be reduced, and so the accuracy would be improved. Like if we take more time steps, I mean more grid spacing, very less, I mean very small sizes of the grids, the system would be more accurate. Like the information from one point to other, the information traveled would be like easily passed and the accuracy would therefore be improved. But on the other hand, consistency and stability given in option 2 and 3 are again more dependent on time step factor as well. So we cannot just give out with grid spacing alone. So these are not statable under this condition. So first statement is the only right answer. Option A 1 only is right. Also answer is option A. Now we will go to question 11. In question 11, it is mentioned that which of the statements is correct about the discretization of one-dimensional unsteady diffusion equation. consistent and unconditionally stable schemes can be developed. FTCS scheme is conditionally stable. One only. Option B, two only. Option C, both. Option D, neither. I would say option C, both, because we'll see in the next slide as well. But forward time and central space we are using for discretizing the one-dimensional unsteady diffusion equation. So we can get conditional unconditionally stable solution we can get, but FTCS scheme is conditionally stable. That's just what we are saying. FTCS is conditionally stable, but on the other hand we can get develop unconditionally stable schemes also. We'll see how. So first is unsteady one-dimensional diffusion equation is given by dou f by dou t plus is equal to a times of dou square f by dou x square, and we are just taking it. But if we use forward in time and center in space explicit scheme, what we would be getting? F of I n plus 1 minus f of I n divided by delta t. And it is on the RHS side, we are having a times of f of I plus 1 n minus 2 times of f of I n at nth time step plus f of I minus 1 at nth time step divided by delta x square. This is expansion for forward in time and central in space. So here it would be like this, delta t would go that side and we would be getting a into delta t by delta x square, which is replaced by sigma, and this is the final equation we would be getting for explicit scheme. So here the most famous condition is like it should be less than or equal to 0.5. So here it is a conditional stability. We are imposing some condition for attaining stability. So FTCS explicit scheme is conditionally stable. But on the other hand, if we use implicit scheme like Crank-Nicolson scheme, we can get unconditional stability as well. So unconditional stability can be obtained, but this particular FTCS scheme is conditionally stable. This is what is given in question 11, that consistent and unconditionally stable schemes can be developed, but FTCS scheme is conditionally stable. That is 1 as well as 2 is true. That is both is the right answer. Now we'll go to question 12. In question 12, which of the following numerical schemes is to be preferred for the numerical solution of a PDE? So for getting a numerical solution of a PDE, which numerical scheme should we prefer? First one, consistent but unconditionally unstable scheme. 2, inconsistent but unconditionally stable scheme. Third one, consistent but conditionally stable scheme. On looking at it, we can say that what we require is we need consistency and stability to achieve the convergence. So consistency is important, stability is important as well. So in the first statement, consistent is there but unconditionally unstable. So here it is like unconditionally unstable, like we do not want that. And in second one it is inconsistent, so it is inconsistent, so again we do not want that, but it is unconditionally stable. Whereas in the third statement it is like consistency is there and conditional stability is there. If it is conditionally stable, we can modify it and we can get the solution, so it is not a problem. So numerical schemes are the following numerical schemes is to be preferred for numerical solution of a PDE. It is consistent but conditionally stable. So option C, sorry, third statement is the only right one. Option A 1 only, option B it is 2 only, option C it is 3 only, option 4 it is not 1, not 2, not 3. So we will prefer third statement, so it is C is the right answer. Let 3 is consistent but conditionally stable. So before going to question 13, now the time is 3:58. We'll just take a 5 minutes break and we'll come back by 4:03. Thank you. So yeah, we'll start now. We'll start with question 13. In question 13, it is given that figure 2 shows the exact solution and the computed solution. That is, exact solution is given by dotted line and computed solution as a function of x at particular time instant. The difference between the two is attributable to truncation error in time, truncation error in space, both neither. So here it is the figure 2, which is showing this is the exact solution and this is the computed solution, so which is a dotted line. So here we are having as a function of x at a particular time instant. Difference between two is attributable to, so here we have truncation error in space and truncation error in time. So this is like the, it is getting in changes in space as well as in time. So the exact solution should have come here and like this, whereas computed solution we are getting it like this. So here there is like this, there is some delay as well as there is some change in values across position. So there is truncation error in time as well as truncation error in space. So both is the right answer, that is option C is the right answer. So we'll go to question 14. In question 14, it is given that for the one-dimensional wave equation, which of the following are true for the forward time, forward space explicit scheme? So for one-dimensional wave equation, which of the following is true for forward time, forward space explicit scheme? First order accuracy, inconsistency, unconditional stability. So this is the question we, okay, that is like forward in time, backward in space. Here it is forward in time, forward in space. But the answer however remains the same because it is first order accurate, inconsistent, and sorry, it is first order accurate is true, it is conditionally stable, and it is consistent. So second and third are false. So 1 is the right answer, B is 1 and 2, C is 1 and 3, D is 2 and 3. Like in the same similar question we saw previously also, in that question what was asked, it was about forward in time, backward in space. However here we are dealing with forward in time and forward in space explicit scheme. So there we saw that how that equation is first order accurate and it was consistent and it was conditionally stable. So similar things can be applied here as well. So it is first order accuracy is true, but here it is mentioned inconsistency, which is false, and it is mentioned unconditionally stable. Again this is false. So answer to this problem is only first one is right, that is first one is given by A. Option B is the right, option A is the right answer. So how? Forward time forward scheme, so it is like dou u by dou t plus alpha times of dou u by dou x is equal to 0. There we have taken the equation on the other side, but general equation is dou u by dou t plus a times of dou u by dou x is equal to 0, and we are expanding it using forward in time, forward in space. So what we are doing is dou u by dou t, we like here this is dou u by dou t plus a times of dou u by dou x at I and n is equal to, we are expanding u of t, that is dou u by dou t using the forward in time. So u I n plus 1 minus u I n divided by delta t, and plus alpha times u I plus 1 minus u I at nth time step divided by delta x. And here we are using the Taylor series. So rest of the terms would be there as well. So what are the terms remaining? Delta t by 2 dou square u by dou t square, that is given by utt at I and n, plus delta x, it would not be, yeah, dou square u by dou x square. Okay, let it be. So dou square u by dou x square, and again del x by del x by 2 into dou square u by dou x square, and remaining terms that we have mentioned it using delta t square and second order in time and second order in space. So the rest of the terms are second order in time and second order in space we have neglected. So here we have given till first order in time and first order in space. So we take this alone and we take the rest of the things to the other side. So we are taking these truncation error terms to the other side, and we have taken it this term to the this side. So here we can say that it is first order in time and first order in space. These are the things we are neglecting. So this particular thing is equal to this if we neglect all these terms. So it is first order in time and first order in space. And then if we reduce the delta t and delta x, it is approaching 0. So the truncation error is approaching 0, meaning that it is consistent. So if delta t and delta x is approaching 0, the truncation error term is approaching 0. So it is consistent. Here, however, the option is given as inconsistent, so which is false. Because delta t and delta x on reduction to 0, the error is also reducing to 0. And it is again, we are neglecting these terms. So here, don't confuse with this, because here along with the first order in space and first order in time, we have neglected the second order in space and second order in time. But however, for forward time and forward space, we would be left out with only these things. So the whole term is taken as a truncation error. Therefore, it is delta t to the power of 1 is neglected and delta x 1 is neglected. So it is first order in time and first order in space. So entire term is first order in time and first order in space. So FTFS scheme is consistent in the limiting case of delta t and delta x tending to 0, and therefore from the option we can say that first order accuracy is true and it is consistent and it is conditionally stable. So like delta t and delta x when modified, it would be giving a conditional stability as well. So one alone is right, which is given by option A. I hope it is clear. Now we'll go to question 15. In question 15, it is asked that which of the following schemes may give assurance of convergence for the unsteady advection equation. So here assurance for convergence. So the equation is unsteady advection equation. So it is given by dou f by dou t plus dou f by dou x is equal to 0. So may give assurance of convergence for unsteady advection equation. So first one is forward in time, backward in space, explicit equation. And second one is forward in time, forward in space, implicit equation. And third one is central in time and central in space, implicit equation. So here it is that all three can give assurance for convergence because explicit schemes are conditionally stable and implicit schemes are unconditionally stable. So stability is there and consistency, because the advection equation we can rewrite it in a form that delta t and delta x on approaching 0, the truncation error would also be approaching 0. So it is consistent as well. So according to Lack's theorem, consistent and stability is there, so it can produce converged solutions. So 1, option A 1, option B 1 and 2, option B 1 and 3, option D 1, 2 and 3. So that is the right answer, because answer is option D. Because unsteady advection equation is given by this. Dou f by dou t plus A times of dou f by dou x is equal to 0. Forward in time, central in space, explicit scheme is given by f of I n plus 1 minus f of I n divided by delta t plus A times of f of I plus 1 at nth time step minus f of I minus 1 nth time step divided by delta x. Why I have given 2? It should be, okay, it is central scheme, so it is 2 times of delta x, and this is explicit scheme. So here we can see that delta t on, like if these terms go other side, and a into delta t by 2 times of delta x would be remaining, and so we can put conditional stability, and this on like truncation error can be reduced to 0 as well, that we have seen in the previous slides also. And forward time, forward in space is given by some modification to this particular schemes terms, and forward time, forward in space, implicit scheme. And here we are using, instead of nth time step, we are using n plus 1th time step because it is an implicit scheme. And forward time, backward in space, explicit scheme, and forward time, central space, explicit scheme. And for implicit scheme, we would be using n plus 1th time step. So here all these are like a simple equation because it is an unsteady advection equation. So we can, on seeing itself, we can say that these are consistent equations, and it can be conditionally stable or unconditionally stable depending on the implicit and the explicit schemes we are using. So explicit schemes from one dimensional equation, so it is like 1D wave equation, and here you are using sigma is equal to alpha times dou t by dou x, and this is forward time backward in space, and forward time central in space, and forward time forward in space. So our unsteady equation is given by this, and like we can rewrite it as this. So in the options what were given, forward time backward space explicit. So this is the equation, we can rewrite it in this particular form. So here we can say that sigma is there, so it is like conditionally stable and the error can be reduced, so it is consistent as well, so it can be converged. And second one is implicit, because here you are using n plus 1th time step. Again here sigma is there, so it would be conditionally stable and consistent as well. Central time central space is given by this. Again here we can use the conditional stability, or it can even be it can be conditionally stable, and it would be like we can say consistency. So since it is stable and consistent, we can say that these things can be converged. So all three from the option are giving the can give converged solutions. We can have an assurance of convergence for all three, but depending getting converged solution or not is the different problem, but we can have an assurance of convergence. So answer is option D, which is mentioning 1, 2 and 3. Now we'll go to question 16. In question 16, it is mentioned that which of the following schemes is only conditionally stable for the unsteady diffusion equation? So which of the following schemes is conditionally stable? So we can say that FTCS explicit, Crank-Nicolson scheme, Dufort-Frankel scheme. So on looking at it itself, we can say that FTCS explicit is a conditionally stable scheme. Rest are unconditionally stable scheme. So option A 1, option B 1 and 2, option C 1 and 3, option D none of the above. So it is conditionally stable is forward in time, central in space. So answer is option A. So how it is that diffusion equation is given by this, by now we are very sure of that. And forward time central space is given by f of I n plus 1 minus f of I at nth time step divided by delta t, and equal to central in space. So we have this particular equation, and so it is like conditional stability, because we would be taking delta t a and delta x into consideration, and that would be giving out some condition. Because it is an explicit scheme, we would be marching in time, so we need to have a control over the time step as well as the grid size. So only then we can achieve a solution. So it is conditionally stable. On the other hand, Crank-Nicolson scheme is an implicit scheme. So we are taking average between. So here also we have used the forward time central space, but we have averaged the terms in the right hand side between time step n plus 1 and n. So it is fi plus 1 n plus 1th time step plus fi plus 1 nth time step divided by 2. So similarly we have obtained the equation, and Dufort-Frankel scheme is given by this fin is given by fin plus 1 plus fin minus 1 divided by 2. So on that we are getting this equation as well. So these are like in implicit scheme where we would be solving for the present time step as well. So the solution would not be varying much with the time step for the implicit schemes like Crank-Nicolson and Dufort-Frankel. So they are unconditionally stable. However, forward time central scheme, this particular equation is a conditionally stable equation. So answer is option A, that is 1 alone is the right answer. Conditionally, FTCS is conditionally stable, whereas these are implicit schemes. The possibility for unconditional stability is there. So FTCS is conditionally stable. Crank-Nicolson and Dufort-Frankel scheme are unconditionally stable, and Dufort-Frankel is unconditionally unstable. So question 17. Which of the following schemes is second order accurate in both time and space for the unsteady diffusion equation? So which of the following schemes is second order accurate in time as well as space for unsteady diffusion equation. So again the options are FTCS explicit, Crank-Nicholson scheme, Dufort-Frankel scheme. So it is asked regarding time and space. So in all, in the first one, forward time and central space, we can see that since it is a forward time, it is only first order accurate with respect to time. For central alone, it is second order accurate with respect to space. So it is false. Crank-Nicholson scheme, although it is similar to FTCS, here we are averaging between n plus 1th time step and nth time step. So on that basis, if we use a Taylor series expansion and put it back in the equation, it would be giving one accuracy higher. So it is second order accurate in space as well as time. Similarly, in Dufort-Frankel scheme as well, we are averaging between two time steps. Therefore, the accuracy is improved to one more order in the time factor. So Crank-Nicholson scheme and Dufort-Frankel scheme is the right answer. So option A 1, option B 1 and 2, option C 1 and 3, option D 2 and 3. So answer is option D, because forward time central space is first order accurate with respect to time and second order accurate with respect to space. Whereas these two methods are second order accurate with respect to space as well as time. So answer is option D. Like diffusion equation, we are using forward time explicit scheme, forward time central space Frank-Nicholson scheme, and Dufort-Frankel scheme. Here we are averaging between n plus 1th time step and nth time step, whereas here we are averaging between n plus 1th time step and n minus 1th time step. So on that basis, when we use the Taylor series expansion and put it back in this equation, we would be having cancellation of the terms because of the averaging. So delta t would be cancelled out and we would be delta t square left with delta t square. So delta t square would become the least power. On that basis, the equation would become second order accurate with respect to time as well. So these Crank-Nicholson scheme and Dufort-Frankel scheme are second order accurate with respect to time as well as space for this particular diffusion equation. So we'll go to question 18. In question 18, for the 1D scalar transport equation with no source term, which of the following will give oscillation-free stable solution with second order accuracy in both time and space? So we'll see the options. So here it is mentioned that we are dealing with a one-dimensional scalar transport equation. That is a generic equation. There is no source term which will give an oscillation-free stable solution with second order accuracy in time as well as space. So first one is forward time, backward space, central space, explicit, and second one is forward time, central space, explicit. So here on looking at it itself, we can say that both are not second order because it is using forward in time. So on that basis, forward in time will give first order accuracy with respect to time. So in that basis, we can say that first statement as well as second statement is false because it is not second order accurate with respect to time and space. They are second order accurate with respect to space here, but it is not with time. So 1 as well as 2 is false. We'll see the options. Option A 1 only, option B 2 only, option C both, option D neither. So in question it is asked which of the following will give oscillation free stable solution with second order accuracy in both time and space. So it is neither 1 nor 2. So answer is option D. We'll just see how to write the equation and how to write the expansion. So second one-dimensional equation, general transport scalar transport equation, one-dimensional scalar transport equation is given by this. So we are having advective term, we are having diffusive term, and forward time, central space and central space is given by. So here we are having one time derivative, one space derivative, and two space derivatives and one time derivative. So it is like with forward time we have this equation and this is central space and this is central space. And for forward in time, backward in space and central in space, we would be having f of I minus 1 divided by delta x, and this is like central in space. So here we can say that forward time and forward space both gives first order accurate with respect to time. So they are not second order accuracy at all, and they can be leading to oscillation. Like it may not give stable like oscillation free solution. uh, but on the basis of accuracy itself, we can ignore the both the statements. That is forward time, backward space, central space, and forward time, central space, both are false because it is using forward in time, which is a first order accurate scheme. So it is first order with respect to time. Whereas in the question it is mentioned that it should be second order accurate with respect to time as well as space. So both of the options are false. So we can neglect both the options. We'll go to question 19. In question 19, it is asked that which of these properties is not included in the Lax equivalence theorem? Option A, stability. Option B, boundedness. Option C, consistency. Option D, convergence. So answer is option B, because we know that Lax equivalence theorem, what it states, it mostly states that when the system is having consistency and stability, it can produce converged solutions. So what is it including in it, the theorem? It is including consistency, it is including stability, and it is including convergence. So if there is consistency and stability in the equation, it can produce convergence. So stability is there, consistency is there, and convergence is there as well. But boundedness, that is between the limits, it does not include in the Lax equivalence theorem. So option B is the answer, because which of these properties is not included in the Lax equivalence theorem? Lax equivalence theorem does not include the boundedness. It is only covering the stability, consistency, and convergence by means of stating that when there is stability and consistency in the system, it can produce convergence. We'll go to question 20. In question 20, it is asked that a solution is ideally converged if the results match with the exact solution, results for two consecutive iterations are same, results for two schemes are the same, and option D, results for different boundary conditions are the same. Like convergence is nothing but between two time steps. If it is giving the same solution, we call it converged solution. Other definition does not mean for convergence. Convergence is nothing but if when there is repetitive result in the for few consecutive time steps, we call it converged. So on the options it is given that option B is the right answer, because in the first one it is mentioned that results will match with the exact solution. So here we are using a numerical solution, and getting an exact solution of the PDE is a difficult task. We do not call that as convergence, but we call it converged when the solution is same between the two time steps or two consecutive iterations. If it is the same result, we call it a converged solution. Option C, it is like two schemes. Two schemes and two boundary conditions does not come into picture for convergence, because they are like giving out a different physics. Whereas in basically convergence, idea behind convergence is that when we are solving the system and we are getting two consecutive solutions as same, we call it convergence. That is what we can do in numerical methods also, right? We will be defining a certain parameter like error or something, stating that it would be calculated between two time steps and two iterations, and if it is below a certain tolerance value, we call the system as converged solution. Similarly, the results for two consecutive iterations are same, we call it solution is ideally converged. And now we'll go to question 21. In question 21, in real, how was convergence defined? Variations are accepted when variation is less than result, when variation falls below a certain acceptable range, when variation is the same as the result. So this is what we saw just now. Like how we define convergence, because between two consecutive iterations, if it is the same result, we call it convergence. How do we know if they are same results? So we will be like calculating error, and if it is the variation is less than a critical tolerance value, we call it converged. So it should be less than certain value. That certain value is what is given in option C. When variation falls below a certain acceptable range, we call it convergence is attained. Whereas in option A, it is variations are accepted. Like if variations are accepted, what do we mean by that? How much variations are accepted? Like it is not given correctly. So A is false. B is when variation is less than the result. Like variation would always be less than the result, because like results between two consecutive iterations would be same, variation should be less. Like, but it doesn't make sense here. Whereas in C, it is variation falls below a certain acceptable range. This is true, because it should be less than a certain tolerance value for it to be converging. When variation is same as the result, variation should not be same as result, right? What do we mean by variation same as result? Like, it is not making sense. So answer is option C. And now we'll go to question 22. In question 22, it is given that which of these statements is wrong? Convergence is applicable for iteration processes. Convergence is affected by accuracy and efficiency. Converged solutions do not vary much with further iterations. Converged solutions are exact. So we need to identify a wrong statement. So in the first one, it is like convergence is applicable for iteration processes. So that is true, because while iterating only, we will be noting whether the result between two consecutive time steps is same or different, how much difference is there. So first one is true. Convergence is affected by accuracy and efficiency. Again, this is true because it is a numerical solution. Like depending on the system accuracy, like the convergence can be attained faster or later, but it would be affected. Like accuracy of the system would be playing an important role in convergence, and converged solutions do not vary much with further iterations. That's what we said. Like between two iterations, it would remain the same. We call it converged solutions. Like do not vary with further iterations. Again, true. Converged solutions are exact. This is false, because we cannot say that converged solution is same as the exact solution. That is a different concept altogether. Like it is not true. Like converged solutions may be different as well, but in like some other factors also come into picture over here. But all three statements are right in this context, whereas in this particular thing, option D is false. Since we are asked to identify a wrong statement, option D is the right answer. Answer is option D. We'll go to question 24. Okay, we have 6 more problems. Which of these iterative processes is unstable, given that epsilon n is the error in the nth iteration? Which of these iterative processes is unstable? What do we mean by stability? Like error should be reduced as time progresses. Like error between this particular iteration and the next particular iteration should be less. Like if error is 5, in the next it should be 4, and next it should be 3. Only then we can call this iterative process as stable. So we'll look at the options first. Option A, epsilon n plus 1 divided by epsilon n is equal to 0.5. Option B, epsilon n plus 1 divided by epsilon n is equal to 0.75. Option C, epsilon n plus 1 divided by epsilon n is equal to 1.25. Option D, epsilon n plus 1 divided by epsilon n is equal to 1. So if error should be reducing with time, epsilon n plus 1 should be less than epsilon n, or at least it should be less than or equal to epsilon n. So if epsilon n plus 1 divided by epsilon n, it should be less than or equal to 1. So epsilon n plus 1 divided by epsilon n, option A, it is 0.5, it is less than or equal to 1. Option B, it is 0.75, again it is less than 1. Option D is also equal to 1, at least it is acceptable. So which is unstable? So option C is unstable because it is greater than 1. So epsilon n plus 1 is 1.25 times of epsilon n, meaning that if error is 10 now, in the next step it is 12.5. That is, error is increasing with respect to time. So that is not a stable solution, so it is unstable. So option is C. Answer to this particular question is option C. We'll go to question 25. In question 25, it is asked that in von Neumann analysis, solution is expanded using Lorentz series, Maclaurin series, Taylor series, Fourier series. So we can remember it in von Neumann analysis, solution was expanded using Fourier series. Fourier series is what we use in von Neumann stability analysis to expand the solution. So answer is option D. Okay, now till now we have seen about consistency, stability, convergence, everything associated with the solution while discretizing the partial differential equations. We have five more questions. In those questions, it is just an outline of about compressible solution for the Navier-Stokes equation. Sorry, Navier-Stokes equations while dealing with the compressible flows. So we'll see the question 1. In question 1, it is mentioned that which of the, I mean, this is like 5 more problems are there. In those 5 problems, we are dealing with the Navier-Stokes equation, solution of the Navier-Stokes equation for the compressible flows. So in question 26, it is asking that which of the following statements is correct about compressible flows? Option 1, any flow involving gas is necessarily compressible flow. Second one, compressible flow equations are coupled but linear. Third one, supersonic flows require either shock capturing or shock fitting methods for solution of governing equations. Option A 3, option B 2, option C 1, option B 1 and 3. So basically 3 is the right statement, 1 and 2 are false. Option A is the right answer because compressible flow here does not refer to the fluid property, rather it is a flow property. So any flow involving gas is necessarily compressible flow. We cannot say that. Since it is a flow property, if the density is not varying much, we can say that it is a incompressible flow as well. Whereas gas, on the whole, if we look at it as a fluid property, gases are compressible. But here we are dealing with the flow type. We can say that compressible flow is a flow property. Therefore, we cannot generalize that all the gas flows are compressible. Gas flows can be incompressible as well if there is a no major change in the density of the fluid. So, and then the second one was all the compressible flow equations are coupled equations but linear. So we have in general continuity equations and the momentum conservation equation. So this is a continuity equation given by dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y is equal to 0. Momentum balance in x direction, it is given by dou rho u by dou t plus dou rho u square by dou x plus dou rho u v by dou y is equal to minus dou p by dou x plus dou times of dou by dou x of 2 mu dou u by dou x plus dou by dou y of mu times dou u by dou y plus mu times dou v by dou y. Similarly, we have the equation in y domain, y direction as well. And if there is an energy conservation, we have that energy conservation equation as well. But what we need to know is these equations are coupled equations because like here and the continuity equation and momentum conservation equations are coupled. Only then we can go with the solution. But are these equation linear equation? No, these are not linear equations. They are like non-linear equations because you can see that here it is rho u square, here it is rho u v, here again rho u v, rho v square. Like it is not a linear equation, it is a non-linear equation. So therefore that statement is also false. And the third statement is giving that about supersonic flows. So in order to understand that, m is the local Mach number at any arbitrary point in a flow field. So for subsonic flows, m is less than 1 and sonic flows, m is equal to 1. And if it is a supersonic flow, we have m greater than 1. In CFD, shock capturing methods are used for computing inviscid flows with shock waves. So shock waves are formed when a pressure front moves at supersonic speeds and pushes on the surrounding air. The computation of such flows is an extremely difficult task because they result in sharp discontinuous changes in flow variables such as pressure, temperature, density, velocity across the shock. So shock fitting consists in locating and tracking the motion of these discontinuities, which are treated as boundaries between regions in which smooth solution to the governing partial differential equation exist. So what is happening is that shock capturing methods and shock fitting methods are used when computing inviscid flows with shock waves. So shock waves are formed when there is a pressure front, it moves at a supersonic speed, like m is very greater than 1, and they push on surrounding air and there is a shock wave formation. So computation of these flows is an extremely difficult task because they have a sharp discontinuous changes in flow variables. And because of that pressure, temperature, density, and velocity, there is an abrupt change. And therefore, shock footing consists in locating and tracking these changes between the smooth flow and the place where it is existing. So, shock waves and shock fitting are the methods used in capturing that. So, what was the option exactly? Supersonic flows require either shock capturing or shock fitting methods for solution of governing equations. So, third statement alone is right, whereas first two statements are false. Because any gas flow, we cannot say it is a compressible flow, and similarly, compressed flow equations are coupled equations, but they are not linear, they are non-linear. Whereas supersonic flows require shock capturing or shock fitting methods. Because they travel at supersonic speeds, we require methods like shock capturing or shock fitting methods, shock capturing or shock fitting methods, while shock waves are formed. Like those techniques are used in CFD. We'll go to question 27. In question 27, which of the following statements is true about explicit McCormick scheme? It cannot be used for nonlinear equations. It cannot be used for viscous fluids. Option C, it cannot be used for unsteady flows. Option D, none of the above. Actually, the right answer to this particular problem is none of the above, because which of the following statements is true about explicit McCormick scheme? It can be used for nonlinear equations because you can see that these equations are nonlinear, they are not linear actually. So McCormick scheme is used, and therefore McCormick scheme can be used for nonlinear equations, and it can be used for viscous fluids as well. So it can be used. And third one, it cannot be used for unsteady flows. It can be used. Unsteady fluid flows almost there, almost we see everywhere. So right answer is option D, that is none of the above is the right answer. It can be used for nonlinear equation, it can be used for viscous fluids, and it can be used for unsteady fluids, unsteady flows. So option D is the right. Option D is the right answer. So in computational fluid dynamics, the McCormick method is a widely used discretization scheme for numerical solution of hyperbolic partial differential equation. This second order finite difference method was introduced by Robert McCormack in 1969. McCormack method is well suited for nonlinear equations, and for nonlinear equations this procedure provides the best result. So McCormack in fact provides the best result for the nonlinear equations. So none of the above is the right answer. Option D is the right answer. So we'll go to question 28. In question 28, it is mentioned that in compressible flow through a duct of constant cross section and with adiabatic flows, which of the following is constant? One, volumetric flow rate. Second, mass flow rate. Third, pressure gradient. Fourth, enthalpy. Option A 1, option B 2, option C 1 and 3, option B 2 and 4. So here it is mentioned that adiabatic walls is mentioned, and compressible flow through a duct of constant cross section and with adiabatic walls which is constant. So volumetric flow rate is not constant because flow would be varying, whereas it is mentioned that it is an adiabatic wall, therefore mass flow rate remains a constant, like mass in and mass out, it remains the same, therefore adiabatic walls is correct. Therefore it is given by 2 is the right answer. And pressure gradient is varying, pressure gradient normally varies during the flow, and enthalpy, although it is an adiabatic wall problem, like internal energy might be varying with respect to the system, because it is in compressible flow there will be energy change as well. And so it is mass flow rate is the right answer, that is option B is the right answer. Answer to this problem is option B. Density of a compressible fluid changes with both position and time, and since it is volumetric flow rate is meter cube per second, uh, it is like, oh, density would be varying, therefore the volumetric flow rate as well would be changing. Mass flow rate is constant because no accumulation occurs. So there is no accumulation. So in turn of that, volumetric flow rate and velocity also changes with respect to position. Therefore, right answer is mass flow rate is the one constant property. We'll go to question 29. In question 29, it is mentioned that the conserved variables that are solved in compressible two-dimensional flows are rho u v w t and rho u, rho v, rho h. Option C, rho v, rho w, rho et. Option D, none of the above. So what is given? Conserved variables that are solved in compressible flows, that is two-dimensional flows. So in general, for two-dimensional flows, what are the governing equations you would be having? We would be having continuity equation. We would be having momentum conservation equation in the x direction and momentum conservation equation in the y direction and energy conservation equation. So we are having four equations. So we will be getting four variables. So what are they? This is like compressible flows and two-dimensional flows. So in the first one, it is like rho u v w t. Like here, one thing is we are having three-dimensional flow variables, velocity variables. That is false, and it is a compressible flow. So it would be like, so we would be solving for rho u rho v, not u v. So again, that one is a false in option A. So option A is false. Option B, rho u, rho v, rho h. And we would not be establishing rho h. Instead, we would be establishing rho et. So answer is option C. Here we would be, although the flow variables are right, energy variable is wrong. So answer is option C. We would be establishing rho v, rho w, and rho et. Option C is the right answer. So we'll just look at the equations once. Continuity equations, we would be having it as dou rho by dou t plus dou rho u by dou x plus dou by dou y of rho b. Because it is a compressible equations, we cannot take the density constant and we cannot remove it out. And momentum balance equation, the x direction is given by this. And momentum conservation equation, momentum balance equation, the y direction is given by this. And from these three equations, we would be solving for rho u and rho v. And energy conservation equation, we would be getting the ET. I should have mentioned, but again, sorry for that trouble. Like from energy conservation equation, we will be getting the ET. So it is rho u, rho v, and ET, or like x direction, y direction. Here, whatever the thing might be, because here we are having rho v and rho w. That doesn't matter, but option C is the right answer. Here we are calculating ET. Let us move to question 30. In question 30, it is mentioned that which of the following statements is true for the evaluation of pressure in McCormack scheme. It is obtained from the continuity equation. It is obtained from the momentum equation. It is obtained from the equation of state. Evaluation of pressure is not necessary for compressible flows. So, how are we evaluating the pressure while applying McCormack scheme? The first one is, are we getting it from continuity equation? No, we are not getting it from continuity equation. Are we getting from momentum equation? Again, this is false. Are we getting from equation of state? Yes, we are getting from the equation of state. Last one is like evaluation of pressure is not necessary for compressible flows. It is wrong because we are evaluating the pressure term as well. So how are we doing that? One dimensional wave equation, let us consider it like this: dou u by dou t plus c dou u by dou x. So McCormack scheme, what it does is like we use a predictor and corrector step in the McCormack scheme. So we generally solve the continuity equation for rho, x direction momentum equation for rho u, y direction momentum equation for rho v, energy equation for et. So after obtaining all this is just an example for McCormack scheme implementation. But in general, for a fluid flow problem, we will be getting rho from continuity equation, rho u from x direction momentum equation, rho v from y direction momentum equation, and energy equation we will be getting et. From these variables, we would be calculating the pressure using equation of state. Like pressure is a function of rho and E, and similarly temperature is a function of rho and E. So we are getting the equation, a pressure value from the equation of state. So the answer is option C. It is obtained from the equation of state. So that's it for today's problem. Thank you. I thank you. Like, if there are any doubts in this in today's session, please ask, and we can solve. We can discuss those as well now. Or if there are no doubts, that is for today's session. We'll meet again in the next week, same timing, unless it is changed before. Mostly, it will be from 3 p.m. to 5 p.m. If there is any change, it will be notified from NPTEL email as well. Or else, that's it for today's session. Thank you, guys. So, if there are any doubts, please ask now. Yeah. Yeah. Thank you. Thank you.
Hello, ma'am.
Yeah.
Yes, regarding this final exams are there, right?
Yeah. Yeah.
So for us, the question pattern will be how, ma'am?
Like, I'm not sure about the question pattern actually. Like, it would be similar like my MCQs mainly.
Okay, similar like our
Similar to assignment
assignment.
problems, MCQs will be there. You will be required to solve those. Mostly computer based exams.
Okay,
Like,
okay,
but the like you should be getting some percentage from the assignments. I mean, score and some score from the final exam. So the end exam, like total score will be computed calculated from assignments as well as the end exam. Some percentage would be taken from assignment, some percentage would be taken from the final exam. That would be mentioned in the NPTEL course website itself. If not, I can say next week. Like, now I'm not sure of the percentage, but it is an MCQ will be there, similar to what we are solving in the assignments, and it is a computer based exam. That only that much knowledge I have on the end exam.
okay, okay.
Yeah, thank you. Yeah, okay. Okay, guys, thank you for attending. We'll see again next week, so we can close the session. Yeah, thank you.